Okay, so now you can see what I'm seeing. We talked about processors, we talked about threads, and here's the thing. Sometimes they use the same resources, sometimes they do not, all right? If you look at the way that languages like C, C++, and Java did multitasking, right? They usually did it by means of threads. And also, I mean, there were some process creations. A lot of times process creation may also mean that, you're using an API in your operating system, and that API, because of its use of, say, C, C++, that type of thing, the API for its own part will also, um, it will serve as a means to use C and C++ to create threads or processes, even if they don't have their own, even if the languages, I should say, and their implementations, their compilers don't have their own native means for creating those implements. The operating systems, since their libraries are written in, those common core languages, they will in effect be trying to make threads a lot. If you look at languages like Go and say Rust, they're doing things a bit differently, right? They don't do so much in the way of locking out resources and making, making certain processes or threads wait. Instead, they do it, they use messaging, right? And so they will then duplicate resources for the newer tasks that need to run, and the duplicate resources could then be shared to whoever needs to run them or run in them without necessarily having to make things competitive, right? You're not saying, well, you can't alter this memory because you may corrupt it. Instead, you're just making copies and the other guys are working within those copies. So in this part right here, inter-process communication, sometimes processes need to discuss things with one another, or maybe they need to, make updates that other processes can use. And so there are a couple of ways to make sure that processes and threads can cooperate, right? So if you take a look here, you have cooperation. If we have cooperative multiprocessing, then we're able to share data with other processes. And that allows us to be able to work in roughly the same allocated sandbox, if you will, right? There are certain design patterns for building software and so forth that do use similar types of methodologies for allowing multi-process programs, all right? So there are reasons why we want to have an environment that allows for cooperation. And those reasons may include things such as being able to share information. We want our information to be up to date. That makes sense, right? We also want the following, something called computational speed up. Now, remember I told you before that when we synchronize, we risk slowing down because the the process or the thread that is lagging, we're waiting for those. And so you have like a, a situation in which you're only moving as fast as your slowest component. And that happens a lot in computer science, both hardware and software, where you have bottlenecks because of that. However, when it comes to parallelism and concurrency, we have a concept called speed up. It's not the same as using faster algorithms, right? Instead, it is the actual performance boost realized by using parallel and distributed implements and allowing for cooperation, but a somewhat asynchronous progress, right? And because of that, um, we're able to keep from having to rely on serial execution or waiting for some other process to finish first before we can move forward, right? We don't have to wait on things like barriers um, to, behave as checkpoints before we go to a next stage necessarily. if there are important changes to memory or storage or even, certain pieces of data that may be traveling back and forth between the processors and other components, we can actually use certain uh, implements to try to update others if that's necessary, other processes, other threads, that type of thing. And sometimes you want to, communicate to a process. Other times you may want to change the memory in which, the various different threads are running. That way they can run with different parameters. But either way, the question of how do we get processes to behave alongside one another when we have multi-processing systems and we're used to segmenting their resources, that's a question that has persisted for some time. And because of that, you have inter-process communication. Now, in many types of um, different uh, multi-processing systems, you're going to have a couple of ways of communicating to other processes. So I kind of mentioned two of them, or I did actually. One of them is by updating the memory. So shared memory. If we know that memory is being shared amongst multiple threads, then we can also understand that if only we were to change the memory that is common amongst all of the threads in a process, or the memory that multiple processes may wish to access, then basically changing that memory will allow us to communicate whatever update to data we have, right? So a lot of times you'll see not just in ordinary processors, but even now, say in graphics cards, you have shared memory alongside all those streaming processors or CUDA cores or whatever they're calling them nowadays, right? And the purpose of the shared memory is to allow for those different processors to run on common resources and be able to make, you know, be able to communicate, even if indirectly, with one another. Now, the second one, and this is becoming all more the norm nowadays, is message passing. Basically, you're sending a message to whomever it is or whatever it is that you want to communicate with, right? So message passing is used a lot in parallel programming, right? And basically, it's not necessarily changing memory, but instead reading and writing data to a shared region, right? And in the message passing model, by contrast, what you want to do is use some sort of actual message, kind of like if you were to, print to a file or something like that. Instead of printing to a file, you're going to instead broadcast a signal or a message to whomever it is that you would like to hear your particular message. All right. So in the shared memory system, in one case, you usually have a region in the address space of the processor or process creating the shared memory segment, right? And that's why I said that a process is a set of resources and the threads that run within them. The set of resources, the memory, is specific to a process, but all the threads running within it run within the same sandbox. So by doing that, they already have access to the same memory. Sometimes you may lock resources so that they will not be corrupted by processes that are, or I should say processors that are running out of sync, right? But at the same time, when it comes to the whole shared memory model, sometimes we want to allow for the memory to be accessed by another process. So this is why we have the concept of shared memory, in which it's not specific or it's not closed down to a particular running process. Instead, it is accessible outside of the immediate context. It has a different memory model so that the data that is in shared memory can actually be used by other processors running code, right? And by processors running code, I mean whatever code that they are running, whether it's parallel or distributed, or if it's a process, if it's a thread, that shared memory model allows for access outside of the original context of a given thread running in that memory or a given processor, I should say process, running with that memory allocated. Okay. So now, yesterday I talked about a producer and consumer, right? Here in this context, right, a producer process produces information that is consumed by a consumer process. Yesterday I spoke about a processor that had access to the overall program and whatever it needed to run. And because of that, it could actually dish out tasks to different consumer processors. Well, in this case, this is not much different. All right. So you have the production of information, and then you have those who consume that information. You might think of it in a parameterized way, right? So if I have a compiler, here's their example, that produces assembly code, which is consumed by an assembler, that could be a case of a producer on one end, the compiler, and the consumer on the other end, which is the assembler, the low-level assembler. The assembler may produce object modules, which are consumed by the loader. All right. So we go from source code to object models to now um, object files that need to be loaded so that they can be run. And the producer consumer problem also provides a useful metaphor for the client server paradigm. Now, remember on last week when I did the whole thing with the server, I showed you a web server when I put it up with my machine, right? And you saw me then access the files um, that were in my machine by way of a web URL that I used with my loopback interface. You saw how the server makes responses to the client's requests. So the client in my case was the browser, but the server was the actual web server itself. So as you can see, the consumer and producer model is quite common in different applications, right? Now, a producer can produce one item while consumer is consuming another. A producer and consumer, they actually, in certain cases, they are synchronized. So the consumer would have to wait on the producer to give the consumer the data that it will run with or the actual uh, communication or message that it wishes to receive so it can continue its own work. So why would we call that synchronized? Well, if I'm waiting on my producer to give me the data that I need or the access to data that I need, then that whole waiting part means that the two are running in sync. They are depending on one another in an interdependent manner. So the overall success of the two running would be contingent on the actual individual roles being realized side by side, not just one processor doing what it was originally assigned to do. All right. So now, moving further on with message passing. Okay. Message passing is a bit different. So we have a mechanism that would allow for us to have one process to communicate and synchronize their actions without necessarily sharing the same address space. So this would be much like either communicating to another or perhaps reading or writing to an opposite area where other sorry about that, other processes can read a different address space with a copy of the message that was sent, right? So here they're using the example of a chat program, right? Um, I believe one time I said to you that in Unix we have a situation where everything is a file, right? And that abstraction from that would be a network socket, where the network socket is a file too, but the nature of that file is that it is the type of file that a machine outside of your initial machine can actually, you might say, read or write to that particular component, which is a lot different from, say, the files on your machine. You would probably be alarmed if somebody else were reading or writing to them. The network sockets of the difference are quite different because they actually allow for you to cross boundaries deliberately. Okay. So a chat program would be a better example of message passing because they send and receive. They also may wait for the other to do its half so that it can somehow receive its message that it's waiting on. And so you have a back and forth process in which messages are sent in one direction and received in another, and then vice versa, just a little time later, because it's the chat. It's peer to peer as opposed to just client and host. So now, if processes P and Q want to communicate, this is in the context of a chat, they send messages to receive, they send messages to and receive messages from each other. So they exchange messages back and forth. There's going to be a communication link that must exist between them. And this link can be implemented in a variety of ways. So let's take a look at how this link implementation would work. So we have the send and receive operations. Those are basically uh, the same. Well, they have a lot of an interrelated purpose with what we would have on other appliances that we wish to send and receive information from so that we can read their data, right? So this may sound like, a chat application, and even while it's not, the send and receive process allows for any sort of, I should say, the send and receive functions allow for any sort of process to be able to communicate in real time with another process, or at least one that is at least one that is able to um, handle requests and also return responses. Okay. So now, here you have a case of these actual files send and receive, and they are the type of files that will send a message to a certain process and receive a message from another process. As you can see here, it says send P message. Over here it says receive Q message. Now, if you look very close, you can now see um, why it would be synchronous, because you're actually running a function to basically complete both activities, right? So that is a good example of, cooperative message passing. But one thing that you have to also remember is that the link in this particular case, it may want to communicate despite not having some sort of main integrated goal. So it's just basically communication. We don't really add or take anything away from that. It doesn't improve your performance in the context of processors running and memory being occupied, but instead it allows us to speak back and forth between processes and do it after the functions have been defined. So now, moving forward, I should probably stop to ask any questions thus far. All right, none. No questions. So let's see. Who gets, and because I have to ask this, I just have to. Um, Let me just stop for a moment.